We are going to start a new chapter, that is chemical equilibrium. What is chemical equilibrium? What do you think that chemical equilibrium is? The chemical equilibrium is basically in which the rate of forward reaction is equals to the rate of backward reaction. In chemical equilibrium, the rate of forward reaction equals to the rate of backward reaction. For example, A plus B are your reactants. They are forming C plus D products. The formation of C and D and the formation of A and B from this C and D is equals to each other. This is the forward reaction. From the reactant A plus B, products C and D are forming, and this is the backward reaction. From C to D, A and B are forming. So, in a chemical equilibrium, the rate of forward reaction and the rate of backward reaction becomes equal. For example, you are taking a container and filling this container with the water. You are opening the tap and water is dropping. You do some hole at the bottom. From that bottom, water is releasing out. The rate of filling the container or the rate in which the water is going out from this container becomes equal. This is called as equilibrium because the volume of the water in the container remains same. Because with the same rate you are filling this and with the same rate water is moving out of this container. Clear? This is called as chemical equilibrium. Chemical equilibrium is basically a type of dynamic equilibrium. There are two types of equilibrium. Static equilibrium and a dynamic equilibrium. Chemical equilibrium is basically a dynamic equilibrium. For example, here you having a block. Force is applied on this side and some type of force is applied on this side. Forward force and a backward force. In this way, this block is in a stable condition, in a static condition, in a equilibrium. This is the static equilibrium. But in a chemical reactions, reactants are moving towards the products and products are moving towards the reactant. So there is a motion. There is no static condition. This type of equilibrium is called as dynamic equilibrium. That's why chemical equilibrium is a type of dynamic equilibrium. As we know, chemical reaction is basically a process in which substances undergo changes in their composition. When the chemical reaction takes place, the composition of the substances changes. Reactant change into the product and the composition change. So there are two types of a chemical reaction: irreversible and reversible. Irreversible chemical reactions and reversible chemical reactions. Let's talk about irreversible chemical reaction. What is irreversible chemical reaction? Irreversible chemical reaction is a reaction in which the reactants proceed or move towards one direction only. There is no reverse formation of the reactants. Here you can see in a chemical equilibrium there is a reverse formation of the reactant, but in an irreversible reaction the reactants only moving towards one direction. The substances only moving towards one direction. For example, you are doing neutralization reaction. As you know, neutralization reaction is a reaction between base and acid. Products are water plus salt. This is an irreversible reaction. You cannot change this water and salt into acid and base. So those reactions in which you cannot convert the products back into reactant, this type of reactions are called as irreversible reactions. This is the example of neutralization reaction. Precipitation reaction is also an example of irreversible reaction. For example, the most common example to form a precipitate is silver nitrate AgNO3 reacting with the salt NaCl and producing precipitates of AgCl2 plus NaNO3. So this is the precipitate. You cannot convert back these precipitates into their reactant. This is also an example of irreversible reaction. In irreversible reactions, products do not reverse back, or their movement towards backward is very negligible. That's why we are saying these reactions are irreversible reaction. Combustion reaction is also an example of irreversible reaction. When something is burned in the presence of oxygen, carbon dioxide and water will form and some energy will release. You cannot convert that carbon dioxide and water back into their reactants. Clear? So these are some examples of irreversible reaction. Next, let's talk about reversible reaction. What is reversible reaction? Reversible reaction is basically opposite of irreversible reaction. In a reversible reaction, you can move back your product into reactants at normal conditions. See some examples. For example, you are forming ammonia from nitrogen and hydrogen. This is a reversible reaction. Ammonia will again move back towards their reactants. Another example, PCl5, phosphorus pentachloride form the products phosphorus trichloride plus chlorine gas. These two products, when react with each other, they will form PCl5 again. So this is a reversible reaction. In a reversible reaction, the reaction proceed in both the directions, in a forward direction or in a backward direction. So this forward and a backward direction at a time is a example of chemical equilibrium. Irreversible reactions do not follow chemical equilibrium. Reversible reactions are following chemical equilibrium. That's why they are moving forward and backward at a time. See some differences between reversible and irreversible reaction. In exam, if the examiner asks about write the differences, so you have to write these basic differences. Irreversible reaction that proceed only in a one direction. Reversible reaction proceeds in both the direction. In irreversible reaction, the products are stable. That's why they are not moving back. But in a reversible reaction, products are unstable. That's why they are moving back towards the reactants, because these products are not stable. That's why they are moving back. In an irreversible reaction, arrow is the complete head like this. But when you are talking about reversible reaction, you write two arrows with the half head like this. One arrow and another arrow, both are with the half heads. Next difference you can write in exams is reactants may be completely converted into products in an irreversible reaction, and reactants never completely converted into products in reversible reaction. These reactants do not completely convert into product. There is some margin remains and the products start to converting towards the reactants. And in the last difference, you can write about some examples. In irreversible, you can write about the combustion reaction, neutralization reaction, and in reversible reaction, you can give the example of ammonia formation, PCl3, and chlorine formation. So you have to write some examples. Let's talk about what are the basic states of chemical equilibrium, how you can identify that this reaction is in a chemical equilibrium. There are two basic states. One is the rate of two opposing reactions become equal. The rate of two opposing reactions become equal. What does it mean? The rate of two opposing reactions become equal. This is the very important term to understand, very important state to understand for chemical equilibrium. What does it mean? Let's talk about with the help of graph. Here, for example, you are writing about rate of reaction. ROR is representing as a rate of reaction, and here you can write time. Okay. In a start, you know that your reactants are in a higher amount and products having 0 amount. When the reaction starts, the concentration of the reactants decreases and the rate of reaction increasing. The times come when the rate of the reactants moving forward becomes constant, and while the reactants are decreasing, product formation will increase, and the time comes when the product formation becomes constant. When the rate of the forward reaction, when the reactants are moving towards the product, for example, your reactants are A plus B. They are moving, they are reacting and forming product C plus D. So when the concentration, when the rate of the forward reaction becomes equals to the rate of the backward reaction, the formation of the product, both the rates to form the product or from product to form the reactants back becomes equal. You can see here both the reaction rates becomes equal. They are at the same line. This is the state of chemical equilibrium. In a chemical equilibrium, the first most important state is the rate of two opposing reactions become equal. The rate of forward reaction, this is a forward reaction, and the rate of backward reaction, both the rates become equal. The speed of the reaction towards product and the rate of the backward reaction towards the reactant becomes equal. Second state of chemical equilibrium, concentration of reactants and products become constant, not equal. I am writing become constant, not equal. What does it mean? That the concentration of reactant and product become constant. This is the second state of chemical equilibrium. Concentration of reactant and products become equal. Let's see with the help of graph. Now this time you have to make a graph, time at the x-axis and concentration on the ordinate on a y-axis. For example, A plus B, your reactants are reacting together. Their concentration is decreasing because products are formed, and the time comes their concentration becomes constant, further not decreasing, and the product C plus D are formed. Time comes when the concentration of the C plus D becomes constant, not further increasing. Reactants stop to further decreasing and the products stop to further increasing. This is the second state of chemical equilibrium, which is saying concentration of reactant and products becomes constant. These two are the state of chemical equilibrium. If the rate of the forward reaction and a backward reaction are equal, then state is chemical equilibrium. If the concentration of the reactant and products becomes equal, then this is the state of chemical equilibrium. Now answer my question. I'm giving you one question try to identify the answer. I am drawing three graphs for rate of reaction versus time and three graphs for concentration versus time. See, graph A between time and rate of reaction. This is a forward reaction. This is a backward reaction. This consider this is a graph A. Okay, next graph B. Graph B is between time, ROR, rate of reaction. ROR I am representing as rate of reaction. The graph is, this is a forward reaction, this one is a backward reaction. Graph C between time and rate of reaction. This is a rate of forward reaction and this is a rate of backward reaction. This is graph B and this is graph C. Okay, next, between concentration and time. This is a forward reaction, this is a backward reaction. Between concentration and concentration is decreasing and the concentration of the product is increasing. Graph B between time and concentration. Concentration of reactants decreasing and the concentration of products increasing. Okay, this is a graph C between concentration and time. Forward reaction and a backward reaction. Now you have to tell me, first tell me between these three graphs of rate of reaction versus time, which one is a correct graph? Taha, can you answer this? Taha?
A wala?
In the first one, yes, in our first one, A graph is correct. B and C graphs are wrong. A1 is correct because I told you when the graph is between rate of reaction versus time, then the forward reaction and a backward reaction becomes constant. So this is the only graph in which both having the same rate, both having the equal rate, not constant, equal rate. The rate of forward and the rate of reaction becomes equal, not constant, becomes equal. Okay, from the second graph, concentration versus time. Hassan, answer this beta, which graph is correct? Between concentration.
A.
Ji, Manal, what do you think? Which graph is correct? Manal, what do you think, beta? Which graph is correct? Ji, Zunaira, which graph is correct between concentration versus time? Quickly answer this, beta. Manahel?
Miss B.
No. As I told you, in a concentration versus time, previously you can see here, I have drawn this graph. I said concentration of reactant and products becomes constant. You can see both are not equal, but both are constant. After some time, they are constant. For example, 2 moles of product or 1 mole of reactant, these concentration of the reactant and products are constant, not changing these concentration. This is the state of equilibrium. But I have asked about between these three graphs and you are saying that maybe this one is correct. Not. All three graphs are correct. A, B and C, all three graphs are correct. Why? Because I said the concentration becomes constant. So here you can see after some time the concentration of the reactant is constant and the concentration of the product is constant. In this graph, the concentration of reactant is constant. Doesn't matter, they becomes equal. If the concentration of reactant and products becomes equal, doesn't matter. You just have to observe that both the concentration are constant. In the third graph, the concentration of the reactant decreasing firstly and becomes constant after some time, and the concentration of the product increasing and after some time start to be constant. So all of three graphs are correct. Clear? So these two states is very important for chemical equilibrium. Rate of reaction becomes equal. Rate of forward and a rate of backward reaction becomes equal in a chemical equilibrium, and rate of the concentration of reactant and the concentration of the product becomes constant in chemical equilibrium. Clear? Let's talk about some characteristics of chemical equilibrium. Some characteristics of chemical equilibrium. Characteristics of chemical equilibrium. Let's talk. There are some characteristics of chemical equilibrium. You must remember, you must learn these. Let's talk first one. Don't forget that chemical equilibrium is a dynamic equilibrium. There is a motion, there is a movement, not static. In an observation, it looks like that there is no reaction takes place because the forward and the backward reactions rate are equal, and it looks like the no reaction is taking place, but the reaction is happening. So, because of the movement of the reactant and the forward side of the reactants and the products. Well, let's talk about the characteristics of chemical equilibrium one by one. The first characteristics of chemical equilibrium is the rate of forward and a backward reaction equals. Forward, rate of forward reaction and the rate of backward reactions becomes equal. Both the rates are equal in chemical equilibrium. Next, the concentration of reactant and products becomes constant. The concentration of reactant and products becomes constant, not equal. It could be equal. It could be equal, but the most important thing you have to observe that they are constant. The concentration of product and reactant becomes constant. Third one is the progress of reaction ceases. In observation, it looks like no reaction is taking place because progress is ceases. Reactants are moving towards the product and products are moving towards the reactant. So for the observer, it looks like no reaction is taking place. But in reality, the reaction is taking place, but at chemical equilibrium, but at dynamic equilibrium. So progress of the reaction is ceases. Next, state is attained by the reversible reaction no matter in which direction the reaction proceeding. Try to understand this. A plus B are forming C plus D. Doesn't matter reaction is starting from which side. It could be start from like this. C plus D are making A plus D. In both the condition, chemical equilibrium is followed, dynamic equilibrium is attained. Doesn't matter reaction starts from which side. If the reactant start from A to B and making C and D, or the reaction started from C to D, C plus D to making A plus D. Doesn't matter reaction starts from which side. The important thing is the rate of the reaction is constant. The rate of the reaction is constant. Next, fifth one. At equilibrium, both reactants and products are present in the same ratio. What does it mean? For example, A plus B are reacting together and forming C. According to these characteristics of chemical equilibrium, the concentration of A plus B will be equals to C. It means at equilibrium, A having 1 mole and for example B having 0.5 moles at equilibrium, and product having for example 2 moles. This is the concentration, this is the concentration of the reactant and products at equilibrium. Doesn't matter what is happening, all the time between the reaction of A plus B and C, always their concentration, their ratio remains same. Clear? At equilibrium, both reactant and products are present in different ratio all the time. For example, A having 1 mole, B having 0.5 mole and C having 2 mole. All of them having a different concentration. When the reaction happening, equilibrium is attained, three of them will have the same this concentration to attain the equilibrium, and you can observe that the concentration of all three of them having different concentration. A having 1 mole, B having 0.5 mole, C having 2 moles. All having different concentration to attain equilibrium, different ratios to attain equilibrium, but always they follow the same concentration to attain the equilibrium. Doesn't matter you are taking how much amount, thousands of concentration of the reactant and in thousands the concentration of product, doesn't matter. Always they attain equilibrium at the specific fixed concentrations. These are the basic characteristics. There are two more characteristics of the chemical equilibrium. That is, sixth one is chemical equilibrium attained at closed vessel. Closed vessel is very important. If you are doing reaction in an open vessel, as you know, in some of the reaction gas is produced. So if the gas is produced and the vessel is open, then gas will release out. So you cannot attain the equilibrium in that type of a reaction. So it is very important that a reaction takes place in a closed vessel. Seventh one, catalyst. The effect of catalyst in a chemical equilibrium. How catalyst affects the chemical equilibrium? As we know, catalyst increases, inhibits or increases the reaction. Which means some catalysts increase the rate of the reaction and some catalysts are used to decrease the rate of the chemical reaction. So if you are adding catalyst to increase the rate of the reaction, A is changing into B. If you are adding catalyst, the rate of forward reaction increases as well as the rate of backward reaction is also increasing. It not happen that only rate of forward reaction increase or the rate of backward reaction increase. Due to the use of catalyst, chemical equilibrium maintain. Only rate increases. Only rates increase. For example, reactants are converting into product and products are going back to the reactant. Their rate speed up. This, for example, this is the normal rate. So they will attain their equal concentration at this point. So due to the catalyst, they will quickly becomes equal. They will quickly speed up and attain the equal amount. Their rate of reaction increases due to the addition of catalyst. Forward and the backward, both the reaction becomes speed up. Next our topic is law of mass action. Let's talk about a little bit what is the law of mass action. We will continue it tomorrow. Law of mass action. What is law of mass action? This law is basically given by two scientists, C.M. Goldberg plus P. Wage. These both scientists gave this law in 1864. According to this law, according to law of mass action that was given by C.M. Goldberg and P. Wade, rate of reaction is directly proportional to the product of active masses of reacting species. According to law of mass action, the rate of reaction is directly proportional to the product of active masses of a reacting species. Those species who are reacting in a chemical reaction, their active masses is basically the directly proportional of the rate of the reaction. What does it mean? It means the rate of the reaction is directly proportional to the concentration of the reacting species. What is active mass? Active mass is basically that portion of the substance which takes parts in a reaction. All the species, all the reactant is not reacting. Some specific portion is taking part in a reaction. That is called as a active mass. In your book, according to your book, active mass is basically the concentration in mole per dm cube. Concentration in mole per dm cube. As we know, mole per dm cube is molarity. So when you are taking concentration as their molarity, then the rate of the reaction is directly proportional to their active masses, to their concentration, that is represented as this bracket, square bracket. So while you are writing the concentration in square bracket, that is represented as their active masses, and you are taking concentration as mole per dm cube. So according to law of mass action, the rate of the reaction is directly proportional to the product of the active masses of the reaction. What does mean product? As you know, when you write about the chemical reaction, A plus B react together and make C plus D. This is a chemical reaction. Chemical equilibrium is attained because this is a reversible reaction. So the rate of the forward reaction, which means A and B are reacting. That's why reaction is forward. The rate of the forward reaction is directly proportional to its concentration, to the concentration of the species. So species are A plus B. So the active mass of A and the active mass of B means concentration in moles per dm cube. If I want to remove this sign of proportionality, then I can write the rate of forward reaction is equals to constant K. This is the equilibrium constant. The constant of forward reaction, the concentration of A plus B. I said the product of active masses. For example, if there are 2 moles of B, so which is showing that there are 2 B, not 1. So you have to write square at the square bracket, because there are 2 moles for the B. This is called as the product of the active masses. Clear? So rate of forward reaction is equals to the equilibrium constant at forward reaction plus the concentration of the reacting species, because the reaction is forward. Next, if C plus D are moving back towards the reactants, then you have to write the rate of the backward reaction, या आप इसे कह सकते हैं reverse, the rate of backward reaction or the rate of reverse reaction. Backward reaction is basically the reverse. So the rate of the reverse reaction is directly proportional to the concentration of the species. So concentration of the species you have to write in a square bracket SCD. Remove this proportionality sign, so you have to write the rate of the reverse reaction is equals to equilibrium constant for reverse reaction, concentration of the species as a square bracket. Their